So this is section 2.2 basic derivative rules. And so last section dealt with using the limit definition of a derivative. So we've talked about the tangent line, where you find the slope of the tangent line, which is the derivative can give you the slope of the tangent line for any particular point. So that was dealing with this formula. This was from section 2.1. And instead of having to apply this limit, there are known rules for finding derivatives of the function, and it makes it much easier and less work. So this section goes over some of the rules that you can apply to find a derivative of a function instead of having to use this limit definition. Now, what I put up on Blackboard down here, it says table of basic derivatives and integrals. If I click on that, this has all the derivative rules that you'll use for if you take Calc 1, 2, or other calculus courses, and then also there's something called integration, which we'll get to towards the last half of the course. But this is the table that has all the rules. All right, so that's on Blackboard under course documents, and it's at the very bottom. Also, if you didn't notice that the unit circle trig rules, that's always a thing that's helpful referencing this. And then you can looking at the unit circle for different values that you can find sine and cosine. All right, so that's available. And I recommend just when you're going through the homework, just having this table open while you do the problems. All right, so this section just deals with some of the rules from that table. And again, we're finding a derivative of a function, and the derivative of a function gives you a different function. And that different function will tell you the rate of change of the original function for any point x, which basically translates into, it can tell you the slope of all the tangent lines that are touching the function, the original function, at any point x. All right, and so that's what the derivative does. And instead of having to use this limit definition that becomes really cumbersome, there's these rules. And in particular, the first rule is called the constant rule. And it just says you take the derivative of a constant, it's always 0. So c is just a number. So the derivative of just a number is equal to 0. And that's pretty much it for that rule. So what's in green is an example demonstrated. So the d dx that is notation for taking the derivative. And what's in brackets is the function in which you're taking the derivative of. In this case, the function's a constant function, it's just 3. All right, and before I go over the other rules, this is just a recap of the notation for derivative that was addressed in the last section. But various notations they'll use. we just saw d dx. They'll also use commonly uses f prime of x, and that's supposed to be parentheses. So f prime of x is how to say that, and that's the first derivative of the function. If there's one quotation mark, that means it's the first derivative. We'll learn later on you can take a second derivative. Another notation is they use y prime, and y is just in place of the function f of x. So where y equals f of x. So the y prime is the same thing as f prime of x. All right, these three are the most common notations we'll see. And then a fourth one that's very common is dy dx. And dy dx is the same thing as y prime. All of these are the same. They're just taking a derivative of the function with respect to x. So dy dx is interchangeable with y prime. And it means take the derivative of y with respect to x. That's what it means. And all of these four notations, they're operators, and they're operators for taking the derivative. They all mean the same thing. Which is taking the derivative of a function. All right, so derivative is an operator, and after you apply the operator, it gives you a function, another function, and that other function is the first derivative of the function. All right, so to continue where I left off there, basically the notation for derivative is going to be d, it looks like a fraction, d over dx, but it's not really dividing, it's just taking the derivative. And then with respect to x is what the denominator part is saying. And then these four things are all equivalent. So you'll see me using them interchangeably. But as far as the derivative rules, the constant rule, derivative of a constant is 0. Like in the example in green, derivative of 3 is 0. The next one is the power rule, and it applies to like a polynomial. So a polynomial is like a function that has variable x, some exponent. And all it says is when you take the derivative of the term that has x to the n, you drop the exponent down, so it becomes n times x, and then you subtract 1 from the exponent. So it'd be n times x to the n minus 1 power. So for example, if I took the derivative of x squared, you drop the 2 down, so it becomes 2 times x, and then subtract 1 from 2, so 2 minus 1, which becomes 2x to the first power, or just 2x. There's a special case of the power rule, and that's the derivative of x, and I would just have this ingrained, just memorized essentially. So hopefully over time, when we do enough examples in the homework and so forth, you'll have these rules memorized, but this one especially. Derivative of x is 1. All right, that's true, and the reason why it's true is I applied the power rule. So you can say derivative of x is the same thing as taking the derivative of x to the first power, and they don't write the 1 for any number, but it's always assumed that there's always a 1 for the exponent. So derivative of x to the first, and then you apply the power rule. You just drop down the exponent, drop down 1 times x to the 1 minus 1. So the power rules, which would be 1 times x to the 0, which is x to the 0, and any number to the 0 power is 1. So that's just an rules with numbers and exponent laws, is that any number to the 0 power is 1, except 0 to the 0. The fourth one's called the constant multiple rule, and also I wouldn't say you have to remember what these are called, just know how to apply them. The fourth one's called the constant multiple rule, and it's just saying if you have the derivative of some constant times a function, you essentially factor out the constant out of the function and then take the derivative of the function. So it's kind of like just factoring out a number and then taking the derivative of the inside portion. So for instance, if I took the derivative of 3x squared, I factored out the 3, and then I focused on taking the derivative of x squared, and then taking the derivative of just x squared, so applying the power rule. All right, and that's, so I just keep the 3 in front, so we 3 times, and then parentheses, I put down what's the derivative of x squared is, which is 2 times x to the 2 minus 1, which is 2x. So it'd be 3 times 2x, which is 6x. The fifth rule is called the sum and difference rules, and it's essentially if you have two functions that you're adding or subtracting together, you take the derivative of the first function plus the derivative of the second function, or the derivative of the first function minus the derivative of the second function. You take derivative of each part. So for instance, if I had 3x squared plus 4x and I wanted to take the derivative of that, I broke it up into its different parts. So this would be like f of x is the 3x squared, g of x is the 4x. So I have derivative of f of x, which is 3x squared, and then derivative of g of x. So the 3x squared, I did this earlier, right? I had this to be 6x, but what the steps were is I factored out the 3 because that's the constant multiple rule, and then took the derivative of x squared. For the derivative of 4x, I factored out the 4. Again, that's constant multiple rule. All right, that's factoring out the 4, and then also I factored out the 3. Then the next thing I did was I applied the power rule to each part, so that x squared turns into 2 times x, because it would be 2x to the 2 minus 1, which would be 2x. Derivative of x is just 1. That's that special case of the power rule. Right, so just have it ingrained that the derivative of x is always 1. All right, so then I combine the two together. So I had 3 times 2x is 6x, and then plus 4 times 1, 4 times 1 is 4. So the result is 6x plus 4. And then the last two rules for this section are derivative of sine and cosine. And it's just the derivative of sine is cosine, and the derivative of cosine is negative sine. So sometimes you might have to rewrite a function into a different format so that you can take the derivative of it. So for instance, if I had f of x equal to 1 over x squared, because I have x squared in the denominator, I can rewrite it as f of x equal to x to the negative 2. So that way it has the structure of x to the n, which means then I can use the power rule. All right, so first thing, I use exponent rules to rewrite 1 over x squared as x to the negative 2, and then I take its derivative. So its derivative of x to the negative 2, you drop down the negative 2, so it'll be negative 2x to the negative 2 minus 1. All right, the power rule is n times x to the n minus 1. So that gives me negative 2x to negative 3. And then the last thing is I'm going to rewrite it so that there's the negative 3 is no longer a negative exponent. And that's just bringing the negative 3 into the x to the denominator, so it changes into x to the positive 3. All right, so some examples you'll have to rewrite it into a format which you can apply the derivative rules. And yeah, that's pretty much all the rules. And at this point, it's just going over examples. So I'll do a couple examples in this video, and then I'll do some more in the next video. All right, so I wrote down these examples. We're going to find the derivative of the following using the derivative rules. So these are the problems 7, 9, and 11, 13, and number 17. All right, so number 7, I have y equals 12. Well, this is just a constant. So I just apply the constant rule. And that's just a derivative of a constant is 0. So essentially applying the constant rule, here I wrote y prime, that's the derivative of y, is equal, taking the derivative of 12. 12 is just a constant. That means it's going to turn into 0. So y prime is equal to 0. And that's basically it. All right, so the next one's y equals x to the 7th power. And so this has the structure of x to the n. I can use the power rule. Where you take the derivative of x to the n, drop down the exponent, so it's n times x to the n minus 1, subtract 1 from the exponent. So in this case, y prime is going to be taking the derivative of x to the 7th, which will be dropping down the 7 to x to the 7 minus 1. That's going to be 7x to the 6th. So y prime is 7x to the 6th. All right, instead of having to write, because it gets kind of annoying having to write dx all the time, instead of writing that all the time, it's going to be understood that I'll jump from y prime to the to this step. All right, so instead of writing dx all the time, unless it helps to write it, I will do the problem like the following. I would write it as just y prime's equal to 7, then x to the 7 minus 1 like that. So I just skip having to write the ddx part, because it's understood at this point that I'm taking the derivative of x to the 7. All right, sorry, you can hear my damn dog in the background. All right, so that's that one. The next one is number 11. I think it was it f of x, or yeah, still y equals, and then 1 over x to the 5th. And so I need to rewrite this into a format because to where I can take the derivative, since I have x to the 5th on the denominator. So I'm going to first rewrite and then take the derivative. All right, so I would rewrite it using exponent rules as x to the negative 5th, and then apply the power rule. Now take the derivative, so y prime is going to equal, you drop down the exponent to be negative 5 times x, and then you subtract 1 from the exponent to negative 5 minus 1, which is negative 5x to negative 6. And then I rewrite this so it doesn't have a negative exponent. So I'm going to rewrite again. So this case, I would put the x in the denominator. So you have y prime is equal to negative 5 up top, and on the bottom you have x to the positive 6. All right, that's how I would do that one. All right, 13, f of x equals the 9th root of x. All right, and this is a case where I'm going to rewrite also. So I'm going to rewrite it into a format that I can take the derivative. So I'm going to rewrite, and I'll use the relationship that if you have the nth root of x, that's equal to x to the 1 over n. So like the cube root of x is equal to x to the 1/3. All right, this is a algebra rule involving exponents and the radicand sign. So for this one, I'm going to rewrite it into f of x equals x to the 1 divided by 9 power. All right, and then I'll take the derivative. All right, since this case I have f of x, the derivative is going to be f prime of x. So the other examples I had y, and I changed it into y prime. So in this case, it turns into f prime of x, and then equals, so I'm going to use the power rule. Because I have an x to some power. So it'd be 1, so I drop the exponent in front of the function, so 1/9 times x, and then I subtract 1 from the exponent, so it's the 1/9 minus 1. So that's going to equal 1/9 x, and then if you do 1/9 minus 1, that gives you negative 8/9. But then I have a negative exponent, so I need to rewrite it. So there's no negative exponent. All right, and that just means I put x in the denominator. So if I put x in the denominator, I'll have 1 over 9, and then x to the 8 over 9 power. So I changed it to where 8/9 is, it's x to the 8/9. That changes the sign from a negative 8/9 to positive when I put it on the denominator. All right, so I think the hardest part of this course isn't necessarily the calculus concepts, it's just knowing the algebra. So you'd have to know from algebra that you have to, that's the rule you use. So if you have some value like a to the negative n, that's equal to 1 over a to the n. All right, so that's an algebra rule with exponents. All right, so that's that one. The next one, number 17. All right, so this case we have f of t, so it's just a different variable. Instead of x, we're using the variable t. Negative 3t squared plus 2t minus 4. So I have these 3 different components, and what I'm going to do is take the derivative of each component. So I'll write it all in detail. So for this case, I'll write the dt notation. So let's see. So if I take the derivative f prime of t, means I take the derivative of the first component. In this case, it's d over dt instead of d over dx, since we have variables t. And then in the brackets, I'll have negative 3t squared. And then I take the derivative of the second component, and that's 2 times t. And then take the derivative of the third component, and that's negative 4 as the third component. All right, so I'm doing this step by step here. So I putting the dtt part to emphasize I'm taking the derivative of each individual component or each term. And so for this one, I could factor out negative 3. That's doing the constant multiple rule. So then I take the derivative of t squared. All right, so I factor out the negative 3. This one I factor out 2. And now I focus on taking the derivative of just t. So these, we're using constant multiple rule. So if I have d dx of c times f of x, whatever the function is, it's going to be c times f prime of x. Basically just means take the derivative, like just factor out the number, the constant, and then take the derivative of the result after you factor out the constant. Now for this one, this is negative 4 is just a number, so I can use the constant rule for derivative. And that's just derivative of a constant is 0. All right, so derivative of -4, since it's just a number, it's just a constant, that turns into 0. So I have plus 0. All right, now this will be equal to and -3, and now I take the derivative of t squared. Well, t squared, I'll use the power rule. So it'll be times 2t to the 2 minus 1 using the power rule. Then I have plus 2, and then I take the derivative of t. That's using the special case of the power rule. Derivative of t turns into just 1. And since the end I have plus 0, you can just ignore that. All right, so I'm just going to leave it like this. So I used the power rule. All right, that's what I used for the t squared. And then I used the special case of the power rule for where it's just t. All right, so just getting ingrained in your head that anytime it's just a variable, whether it's t or x, just a variable like that, then it's always going to be 1. All right, really I am using the power rule, but it's just a special case, just memorizing that, well, I just have the variable t here. So the variable just t turns into 1. That's why I have 2 times 1. All right, so I'm almost there. Now it's just a matter of simplification. So I do -3 times 2, which is -6. And then t to the 2 minus 1 is the first power, so it's just -6t. And then I have plus 2, right? Because that's 2 times 1. All right, this is the end result. So the derivative f prime of t is equal to -6t plus 2. All right, so that was one where I took the derivative of each component and I applied the constant multiple rule to factor out the -3 and then factor out the 2 for the middle term. The last term is just a constant since it's -4, just a number, and a derivative of just a number, it's no variable, just is 0. So that turned into 0. For the t squared, I used the power rule. So that's 2t to the 2 minus 1 in parentheses. And then for just the t part, derivative of t is 1, because that's using the special case of the power rule. And from there, it's just simplifying. So I did -3 times 2 to get -6. And then t to the 2 minus 1 is just t. And then plus 2 times 1, which is plus 2. All right, that's how I would do it in detail. Once we get more used to it in a shorter way, really it's just skipping some steps. I would do it as the following. I did it this long way step by step, so it's showing every single step applying at the particular rule that for each particular step. So I would do the problem as the following. All right, so the original problem was f of t equal to -3t squared plus 2t minus 4. So after this section, later sections, I'm going to do it like this. So f prime of t. And I know I have to take a derivative of each component. So for the first term, -3t squared, it's like I factor out the -3, and then I worry about taking the derivative of t squared. Well, derivative of t squared, that's 2 times t to the 2 minus 1 using the power rule. And then the middle term plus 2 times t, I factor out the 2 because of the constant multiple rule and worry about taking the derivative of just t. Well, derivative of just the variable t turns into 1. All right, because that's the special case of the power rule. And then the last term's just a number. It's just a constant. So the constant rule makes the derivative of -4 turn into 0. So it'd be plus 0. All right, so then that's going to give me -6t plus 2. All right, this is how I normally would do it after this section, but you see how I didn't write in detail step by step like this with all the different ddt's. I was just doing that to show how to emphasize you're taking the derivative of each component and based on each case. First case was -3t squared. I factored out -3 and worried about taking the derivative of t squared. So taking that derivative, that was using power rule. All right, and then the factor out 2, and I just worried about taking the derivative of just t. That just turns into 1, because that's the special case of the power rule. And then the last term is just a number. So it's just -4, and the derivative of that is 0, because that's using the constant rule. All right, that's how I did for each component. All right, so that's where I'll stop the video. I'm going to make a part 2, just doing more examples, more like 17, where it's a function consisting of like multiple terms. All right, so hopefully over time, by doing a bunch of examples, you will get used to the rules.